Greetings from Majinbu Lectures. In this presentation, we will be discussing the concept of Raman spectroscopy of graphene and its related materials. Graphene, as we all may know, has become very penetrable in quite a lot of applications ranging from flexible electronics to water purification, deionization, batteries, and many other applications, especially owing to its excellent mechanical, electrical, thermal, and other properties. Furthermore, this material is being widely used for engineering applications as mentioned, thus making it an engineer's material also. As far as, in order to understand the nature of the graphitic material, it is necessary to comment on its quality and many other aspects for which the Raman spectroscopy is widely used. In terms of the classical physics concept, the Raman spectroscopy can be visualized as follows. For instance, in any kind of spectroscopy technique, the idea is that you have a system and you apply some kind of an electromagnetic wave possessing some energy, say some mu or any other energy like that, and there's going to be a resultant output which is going to have some changes. Now the resultant output that we are going to get is going to be representative of the system that is being described, and that is widely the concept of any kind of spectroscopy. As far as the Raman is concerned, we can explain it in terms of to explain it in terms of classical physics. Say you have an electromagnetic wave oscillating as follows. This electromagnetic wave can interact with a molecule. A molecule is going to possess some dipole moment, which is essentially separation of charges as in the molecule by some distance. It can either possess a net dipole moment or it can have a zero net dipole moment. But irrespective of that, when this molecule is going to be placed within or in an electromagnetic field, what happens? The electron cloud associated with the molecule or the atom is going to undergo some kind of an oscillation. So, mathematically speaking, this is going to be, or even physically speaking, this is going to be a product of the tendency of the molecule's electron cloud to oscillate with the electromagnetic wave that is, subjected for interaction, and that is represented by the dot product of the polarizability tensor and the electric field. The polarizability is a property of the molecule that has the ability to undergo, electron cloud oscillation or polarization on its interaction with the electromagnetic field. Now, this electromagnetic field, as can be seen, is essentially a periodic function which can, say, most probably be represented by a cosine function. Similarly, the oscillations associated with the electron cloud can also behave like a cosine function and can be represented as follows. So the product of these two terms are going to give three subsequent terms, which say is going to one which is going to possess the same energy as the incident electromagnetic wave. The next might possess an energy that is lesser than the incident electromagnetic wave, and the other might possess an energy that is greater than the electromagnetic wave. So these output can be, categorized as Rayleigh scattering, Rayleigh, Stokes scattering, or the anti-Stokes scattering, where the Stokes scattering is going to possess energy that is lower than the incident energy of the electromagnetic wave, and the anti-Stokes is going to possess some energy that is greater than the incident electromagnetic wave. Now, in case of Raman, the thing that is of interest is essentially the Stokes and the anti-Stokes scattering, which is going to possess some energy lesser or greater than the incident energy, which gives information about the system that is being studied. So, although the Rayleigh scattering is the most prominent uh, mode of scattering that occurs in case of any scattering process, generally notch filters are used by the existing Raman instruments in order to cancel out the contribution from the Rayleigh scattering, and mainly the Stokes and the anti-Stokes are observed. Here again, it may be noted that the Stokes component is the one that is contributing majorly uh, amongst these two. And in the presentation that we will be discussing, it is whatever we discuss are with respect to the Stokes and not with anti-Stokes unless otherwise mentioned. While that was the classical physics description of what Raman spectroscopy is, in terms of quantum mechanical perspective, you can view an atom or a molecule, and the bond associated with the molecule is going to vibrate according to the anharmonic oscillator model. So apart from the electronic transitions that are present in the energy structures, energy band structures, you're also going to have the transitions associated with vibration energy levels. So if the energy of the incident photon or the electromagnetic wave is same as that being scattered or vice versa, then there is no energy that is absorbed or lost to the system, and that can be categorized as Rayleigh scattering. On the other hand, if the energy of the incident wave is, or the electromagnetic wave is greater than the resultant you know scattered rays, which probably on interaction with the system has gained some energy, and thus might have resulted in the output or the emission scattering light, electromagnetic wave having frequency lower than the incident one, then you call it the Raman Stokes. On the other hand, if the energy of the emitted or the scattered light is lower than the sorry, is greater than the energy of the incident electromagnetic wave, then you can categorize as anti-Stokes scattering. While that was with respect to the electromagnetic wave, you should also consider something that is characteristic in a solid, that is vibrations in a solid. Now quantization of these vibrations associated with the crystal lattice structure is named as phonons, and the phonon photon interaction is going to play an immense role, especially in case of Raman spectroscopy or understanding the crystal structure or these kind of solid materials, the crystal material. That is, say the photon is going to excite an electron from the conduction band to the valence band. Now, the excited electron might involve in some kind of inelastic scattering with a phonon, such that the electron, say, that has got excited to a particular level will come to an energy that is lower than the initially excited state, resulting in a release of a phonon energy. Now, this uh, electron in the second excited, that is in the resonant state, will again come back to the conduction band along with the release of the phonon energy as mentioned. Now, this energy that is released is representative of the vibrations associated with the solid, and you know gives information about the crystal structure. So while whatever we had described till now is you know a prelude to the Raman spectroscopy, we'll be discussing these concepts in much detail, wherein the discussion is mostly going to encompass the um, information collated in this excellent review article on Raman spectroscopy of graphene based materials and its applications. So, I really encourage the viewers to also go through this article where they have given an exhaustive description of the Raman spectroscopy for graphitic materials. So the aspects that we'll be discussing in course of this lecture series is, with respect to the origin of bands. Now, as I had mentioned in the initial slides, graphene as a material is being widely used for a lot of engineering applications, especially electrochemical energy storage devices, electrochemical sensors, fuel cells, and whatnot. Now, while most of these works are carried out on an engineering perspective with an application focus, you will have Raman spectroscopy mentioned in, say, the research papers, just giving a glance of the quality of graphene that is being used. While that is fine, it is very helpful to get a physics oriented perspective, that is the electronic transition perspective of the associated G band, D band, and the other bands that occurs in this kind of Raman spectrum of graphitic materials. While this is what we'll be dealing with the first lecture, following this, we'll be discussing about the influence of disorder, defects, and number of layers of graphene, on the Raman spectrum, how we can comment on this. And next is that how we can deconvolute the Raman spectrum to obtain the associated diagnostic information. And lastly, the application of Raman spectrum for the graphitic materials and its device development application. So, before we proceed into the understanding the physics or the electronic transition associated with the D or G bands, it is helpful to get a glance of the band structure of graphene. So, the graphitic materials or graphene, say the one layer graphene, can be consists of a unit cell made up of just two atoms A and B, which has a bond length of almost 0.142 nanometer. Now, in case of say a two-layered graphene, the arrangement is such that the layer that you know uh, that stacks above the existing layer is going to have its atom positioned in such a way that it is filling the gaps of the existing hexagonal structure when seen from the top view. And these layers are generally oriented by 60-degree rotation, and they have an interlayer spacing of almost 0.35 nanometer, which happens to be the most common stacking arrangement in two-layered graphene, called the AB stacking arrangement. Now, in order to understand the band structure, it is helpful to have a glimpse of the first Brillouin zone associated with the graphitic material. So, even in the reciprocal space, it so happens that they form a hexagonal structure. And the before I just give up the points, I'd like to discuss the construction of the first Brillouin zone. Say you choose a particular origin point as from shown here, and you connect the you know to the most nearby reciprocal lattice points, and you make some lines, and you essentially draw normal to that. So I'll just repeat it once again. So you draw a line to the most nearby points, and you draw normal to that, as seen here. Again, normal, a normal, then you draw a line, a normal to that, you draw a line and a normal to this, and you draw a line from here to here and a normal to this, and the area that is being enclosed within this structure or is the primitive cell associated with the reciprocal space, and this happens to be the first Brillouin zone. Now, the first Brillouin zone has, again, you have a gamma point at the center of its primitive cell. Now, you have a point at the middle portion of the hexagonal side called the M point, which happens to be the center of the hexagonal edge, and the vertices or the corner points is termed as K and K dash points. Now, familiarizing with these lexicons is going to be helpful in the future slides, as will be seen. Now, the electronic band structure of graphene is very peculiar, as can be seen from the structures here, because for a one layer graphene, it's going to possess a linear electronic band structure which crosses at the Fermi energy level. Whereas for the two-layered graphene, you're going to have a parabolic shape near the Fermi level, and a three-layered shape is going to have a superposition or the combination of the first layer, one layered and the two layered AB stacking, one layered graphene structures. Now, uh, uh, while that was with respect to the band structure, as far as the phonon dispersion is concerned, the one layer graphene is going to consist of six phonon modes, which are further classified as acoustic and optical phonons. And the lattice vibrations of the one layer graphene can be expressed in terms of this following equation, which again consists of acoustic phonons, the A2U and the E1U mode, and the optical phonons with the B2G and the E2G mode. The acoustic and the optical branches are further, you know, categorized into longitudinal acoustic, in-plane transverse acoustic, and out-of-plane, acoustic phonons. Similarly for the optical phonons. So when they mean by in-plane, it is essentially you have a hexagonal structure, and the thing which is this is in-plane longitudinal, and this is in plane transverse, and the out of plane mode is essentially, this is the out of plane acoustic or the optical phonon. Now with this uh, you know familiarization of the uh, terms as described below, as just described, we'll now proceed to understand the Raman spectroscopy of a single layer graphene or monolayer graphene. So, in case of a single resonance Raman scattering, what happens is that you're going to have on interaction of the electromagnetic wave, the electron from the conduction band is going to excite to the valence band, and the excited electron on interaction with the in plane lattice vibrations, which we refer to as E2G lattice vibration, results in some kind of electron phonon coupling, and it comes to the particular state C, via which it again comes back to A, resulting in the electron hole recombination. Now, this process is called the single resonance Raman scattering, and it is satisfied by the G band, as we'll be seeing in the later slides also. Now, as far as the double resonance Raman scattering is concerned, what happens is that you have the excitation of electron from the conduction band to the valence band. Now, following this excited state, it interacts with the phonons and is scattered, undergoing scattering called the inelastic scattering, and assumes the state C. Now, beyond this, state C, it again interacts with the defect present in the material to come back to state D, wherein it undergoes electron hole recombination. Now, here it may be noted that the process, the one phonon first order Raman scattering has occurring here, that is a forbidden state and that is not seen in the Raman spectrum. And hence, for you to, activate this double resonance Raman scattering, it is necessary for defects to be present in the structure. While in this case, you can see that the involvement was like initially the phonons interacted with the excited electron, resulting in elastic scattering, followed by interactional defect. It can also be the other way around, wherein the excited electron can interact with the defect present in the structure, followed by interaction with the phonon, resulting in again one phonon second order Raman scattering. While these processes involved, defect and the phonon, it can also be such that two defects can involve in the, excitation and the subsequent electron hole recombination, resulting in again a double resonance Raman scattering, but in this case a two phonon second order Raman scattering. On the other hand, you have a triple resonance Raman scattering, which is observed only in case of a single layer graphene, because in this case, what happens is that you have an electron that gets excited from the state A of the conduction band to the valence band, resulting in formation of hole here and the formation of excited electrons here. Now, this excited electron is exhibits inelastic scattering, experiences inelastic scattering with a phonon here. On the other hand, the hole again experiences an inelastic scattering with a phonon from the conduction band. Here it may be noted that the wave vectors of these two phonons are more or less similar, and the resonant states are at C and E, wherein the excited electron then recombines with the hole, resulting in the electron hole recombination, and this process is referred to as a triple resonance Raman scattering. While whatever we had discussed till now can be seen with respect to just or within the same Dirac cone, uh, uh, the processes are called as intra-valley processes. On the other hand, say if the resonant states are associated with two inequivalent Dirac cones. Now, when I say Dirac cone structures, these are the band gap structures of one-layer graphene. You have the corresponding resonance process referred to as inter-valley process, which is shown in the next slide, as can be seen here. Here, similar to the B2E transitions, that is, intravalley double resonance processes and triple resonance processes, you can have the intervalley process that take place, wherein again you have an electron excitation from the conduction to the valence band, following the interaction with the, valence to the conduction band, following the interaction with the um, you know interaction with the phonons and followed by defect. Similarly, valence to conduction band and interaction with defect followed by phonon. Similarly, phonon-phonon interaction and a phonon-phonon triple resonance process. These all occurs with respect to the inner, intervalley process. On the other hand, you also have the outer intervalley process associated with the processes that are analogous to the ones that we had just discussed. Now, whatever we had discussed were and where some familiarization with the double resonance and the single resonance Raman process. However, the subsequent slides will actually connect them to the origin of the G band, the D band on a more electronic perspective, electronic transition based perspective. Now, as mentioned, the G band is essentially a single resonance Raman process where you have the excitation of the electron from the valence band to the conduction band, followed by interaction with the in-house, in-plane lattice vibrations, which results in the recombination of the hole with the electron, called the electron hole recombination, and this results in the origin of the G band. On the other hand, with D band, you also refer to as the intervalley one phonon double resonance Raman scattering, wherein you have the electron that gets excited from the valence band to the conduction band, followed by interaction with a phonon or a defect, and the subsequent recombination of the hole with the electron, excited electron, to result in this D band. Now, the D band that you can see is essentially an asymmetrical profile, like which can be fitted by two Lorentzian subpeaks, because the D band is a one layer graphene, which is essentially a resonance of these two processes. It can either be a phonon first followed by interaction with defect, or a defect first followed by interaction with the phonon. Here, it is also worth noting that the D band is essentially, obtained or contributed from the intervalley inner double resonance process, because these are mainly contributions from the K gamma axis that we had, initially seen from the first Brownian zone, and the ones with respect to the outer intervalley process occur along the Km axis. However, studies indicate that the main contributions from the K gamma axis are the ones that uh, you know uh, takes part in the formation or the origin of the D or the 2D bands, and hence the D band can be attributed to the intervalley inner double resonance process. Also, here as noted, you require the presence of a defect for the D band to occur. However, in case of 2D band, you don't need a defect. You just have this, triple resonance process that can take place, wherein you're going to have a two phonon, not a triple resonance process, a double resonance process, wherein, you have this two phonons interacting with the inequivalent K and K dash, resulting in formation of the 2D band. As far as the D double dash peak is concerned, you have a phonon at the LA branch, which is the longitudinal acoustic branch, that can be activated by the defects in the intervalley double resonance process. Also, the D plus D dash combination peak that is seen at around 240, 2400 centimeter inverse wave number occurs because of the intervalley two phonon double resonance Raman scattering, as seen here. While these were all with respect to the intervalley process, the D dash peak, which occurs at 1620 centimeter inverse, is attributed to the intravalley one phonon double resonance Raman scattering process, wherein this occurs because of scattering associated with the longitudinal optical phonon and one defect point. Now the 2D dash peak is a overtone of the D dash peak, which results in a two phonon double resonance Raman scattering, and you don't require defects for its or presence or exhibiting a 2D dash peak, whereas for D dash peak you require a defect. While we had now discussed the Raman spectral bands such as the D band, G band, and obtained, an electronic transition based perspective of these uh, Raman spectra for a one layer graphene, we'll now proceed to get some details about the Raman spectra of a multi layer graphene. So here we'll again discuss mostly the two layer graphene structure and not more than that, because of the associated complexities in the band gap structure and the phonon dispersion characteristics for higher layered graphene structure that we'll discuss in the next lecture. Now, in case of a two-layered, graphene, you're going to have stacking of two graphitic layers, and the G mode or the G band is further divided into a symmetric and an anti-symmetric mode, wherein the nearest neighbor atoms say they are moving against one another, but the movement is such that it is in phase with the two layers, that is the top and the bottom layer, and you call it the symmetric mode. On the other hand, the antisymmetric mode is going to have neighboring atoms that are moving along with one another, but on the whole, they are out of phase between these two layers, and you categorize it as the antisymmetric mode. Now, uh, the I'm sorry, here's Timo. Now, as mentioned, with increasing number of layers, the complexity is going to further increase, and the phonon dispersion characteristics are going to, not be the simple equation as we had seen in the initial slides, but it is a combination of acoustic and, optical phonons in terms of the increasing number of layers. So that is an something that needs to be noted. Now, as far as the high frequency Raman spectrum is concerned, for a multi-layered graphene structure, so here again, say we try to understand it with a two-layered graphene structure. What happens is that you have something called the 2D band, as seen, which is essentially a two phonon double resonance process that occurs at a high frequency or a wave number of around 2600 to 700. Now, for a two-layered graphene, it can be further deconvoluted into four different, Laurentian peaks. It can be fitted using a four Laurentian peaks. And the electronic process associated with that is as shown here. Now, the transverse optical phonons that involves in the interaction with the electromagnetic wave has two symmetries in case of two-layer graphene, T1 and T2. So the four Laurentian peaks, it so happens to be T1 to T1 transition or T1 to T2 transition. Similarly, T2 to T1 transition or T1 to T2 transition as seen. So that is what actually confers via this four Laurentian subpeaks that we are obtaining. Now, this is with respect to the high frequency mode. The ultra low frequency mode is actually a bit more, interesting. So here, this is what we had discussed. You have the C mode that was shown in this particular case as seen here, which occurs at a very low frequency or a low wave number, 43.5. So this one, it is observed that before I tell the trends, we'll just familiarize ourselves with what is a C mode. A C mode is essentially the one associated with the shear in-plane interlayer vibrations of rigid atomic layers. So what happens, it represents the shearing vibrations associated with the interlayer structures. While this is for C mode, the layer breathing mode is the out of plane interlayer vibration as seen, associated with the C axis. Now, in order to understand this rigid layer vibrations, they have been modeled as a set of balls, that are attached to one another, like, one another. And this is or known as the linear chain model. So from this study, it was seen that the frequency associated with the C mode, it decreased with increasing number of layers, but the frequency associated with the G mode, that actually remained the same. Moreover, what can be seen is with the increasing number of layers, one could observe the increasing asymmetry associated with the C mode, but the G mode was quite same, and it can be fitted with the same Laurentian fitting, whereas the C mode, because of the increasing asymmetry, it was fitted by a peculiar structure called the uh, you know um, fanoline shaped with increasing end. Now, in order to get a, while we had discussed the G band to be the uh, single resonance Raman scattering, the question that eventually arises is, does the energy involved, say the electromagnetic energy that we are providing, only at a resonance, only at the energy that satisfies the resonance condition, does that only contribute to the G band, or do we have contributions from the others also? So for this, they had used a resonance Raman spectroscopy, wherein in case of resonance Raman, what happens is the electromagnetic wave or the incident wave is going to have an energy that is similar to the energy associated with electronic transition. And say because of some, uh, and you're going to have the nuclear displacement that is going to be along the direction of the electron displacement. Now, the others are attenuated, and only some particular vibrational modes are selectively enhanced, whereas the others are, not. So, with this resonance Raman spectroscopy, what was done was a particular study was conducted wherein they wanted to comment whether the incident, electromagnetic wave possessing energy that is similar to the resonance energy is what is contributing to the G band, or do we have interference from the other energies also? So the issue is that in a single layer graphene, in an undoped structure, the Fermi level is, close to zero, and you don't observe the involvement from the other uh, energy levels. But what was done in the study was they had doped the structure with holes, resulting in a dip in their Fermi energy level. Now, following this, an energy greater that satisfied the band gap difference was provided between the valence and the conduction band. And what was seen was, with increasing energy till a particular value, which is the resonance energy associated with electron excitation energy associated with the resonance process, one could surprisingly see an increase in the intensity of the G band, following which it decreased. Now, if the excitation wavelength or energy that matches the resonance energy was the only one to have contributed to the G mode, then we should get a graph that is like this. Like, it should be lower till this region, and it should be higher only in this region, and it should be low in the other region also, like something close to this. But it was surprising to note that they could observe uh, increase till a particular value, then a dip. So this was actually discussed or understood in terms of the phase differences, wherein it can be seen that at energy lower than the excitation energy, the uh, processes that are in the opposite phase, they are getting attenuated, and as such or blocked, and as such the intensity of the G band increases. However, on an providing an energy that is greater than the uh, you know resonance energy, the processes that are uh, you know um, constructively interfering are getting blocked, and that may result in the dip in the value. Overall, it is indicating that the different Raman pathways are involving in the G band creation, and it is essentially an interference of the different Raman pathways to result in the G. Now, while this is in case of a single layer graphene, in case of a multi-layer graphene, you have actually the phanoresonance, that is the quantum interference between the phonon modes and or the C mode and the electronic transition that can be seen near the K point. Now that can be results in an asymmetry for bulk graphitic structures, which is seen for C mode, but the G mode remains same, and it is fitted with only the Rolandian peaks, which has been actually linked to the interference effects between the phonons and the electronic transition. So while we had actually discussed in this presentation the uh, uh, the